All right, so last unit, unit 7, is all about waves. So we're going to talk about mechanical waves and electromagnetic waves. Mechanical waves are waves that require matter, electromagnetic does not. In this unit, we will also talk about sound and light, and we'll talk about the anatomy of the ear and the eye. So lots of cool information to learn in this unit. But the first thing, we need to understand what waves are. So, a wave is just a repeating movement that transfers energy through matter or space. The waves will carry the energy without actually transporting any matter. It's just energy that's moving. All waves are caused by something that vibrates. The medium is just the material through which the wave travels, and it could be a solid, liquid, or a gas. But not all waves require a medium to travel. For example, light. Light does not need anything to travel through. It can travel through a vacuum, right? There's really not much between us and the sun. There's just 93 million miles of really not much at all. So light can travel through a vacuum, and a vacuum just means absence of material. Mechanical waves can only travel through matter, so they have to have matter. Transverse waves are waves in which the medium moves at right angles to the direction of the energy of the wave. So you can think about transverse waves as moving up and down. So if you tie a rope to something and you start to shake it up and down, that's going to produce a transverse wave. Longitudinal waves, sometimes called compression waves, the matter moves in the same direction as the energy. It's parallel to the energy. So these move side to side. So transverse is up and down, longitudinal side to side. A surface wave is kind of a blending of transverse and longitudinal. So we can see where it has this up and down pattern, like a transverse wave, but also we can see where it compresses down and then spreads apart, like a longitudinal wave. If you have something standing on a surface wave or in a surface wave, the object itself is not going to move because remember, waves only carry energy. So if you look at this little yellow dot here, this little yellow dot, all it's doing is just kind of rocking back and forth. It is not moving at all. So we have different terms to identify different parts of a wave. On a transverse wave, the highest part is called the crest. The lowest part is called the trough. In a longitudinal wave or a compression wave, the compression is where the matter is close together. Rarefaction is where it's spread apart. Wavelength is the distance between one point on the wave and a point just like it on the next part of the wave. Now, we use this symbol here, lambda. This is the Greek lowercase l. To do this symbol on your note page, up at the top of your Kami page, at that little ribbon, click the button that says FX. So you'll click the button that says FX. A little box will pop up. Once that happens, click the pi symbol. So click the pi symbol. After you do that, the lambda is the third symbol on the second row. Okay, so FX to open the math editor, then pi to get the symbols, and then lambda is the third one on the second row. Now, wavelength is just like any other length, so its unit is the meter. So on a transverse wave, you can measure from crest to crest or trough to trough. For longitudinal waves, you measure from compression to compression or rarefaction to rarefaction. Frequency is the number of waves that pass a fixed point each second. So the number of waves per second. And that's what the unit is. The unit is 1/seconds or hertz. So Hz, that's hertz. And it's named for some guy, so that's why we capitalize it. The period is the amount of time it takes for one wavelength to pass a point. So period is the time, frequency is the inverse of that, 1/the time. As frequency increases, wavelength decreases. So looking at these two diagrams here, they're traveling for the same amount of time, but we see this one, the frequency is much more, meaning its wavelength is less compared to this guy. So frequency is the number of waves that pass by per unit of time, and wavelength is the length between equivalent points on the wave. Wave speed is how fast the wave is moving. Wave speed is equal to wavelength times frequency. Wavelength times frequency. The unit of wave speed, just like any other speed, is meters per second. Light travels faster than sound waves. Light travels at 300 million meters per second. Sound travels at 342 meters per second. So light is significantly faster. Light travels faster in gases and in a vacuum than it does in liquids and solids. The opposite is true for sound. Sound travels faster in solids and liquids than it does in gases. For a mechanical wave, amplitude is a measure of the energy of that wave. How much has that wave disturbed the medium? So the more energy a wave carries, the greater the amplitude. Longitudinal waves, the amplitude is how close the compressions are, how close the medium is at the compression. For a transverse wave, the amplitude is the height of the wave. All right, so we're going to do some practice now. All right, so wave speed is wavelength times frequency. So wave speed, which has a unit of meters per second, is the wavelength, which has a unit of meters, times the frequency, which has a unit of hertz. So wavelength times frequency equals our wave speed. So number one says a water wave has a frequency of 2 hertz and a wavelength of 5 meters. What's the wave speed? So wave speed equals wavelength times frequency. So in this case, the wave speed is 10 meters per second. Okay. Number 2 says a wave has a speed of 50 meters per second and a frequency of 10 hertz. What is the wavelength? So wave speed equals wavelength times frequency. We need to get wavelength by itself. To do that, we divide both sides by 10. And when we do that, we see wavelength is 5 meters. Okay. Number 3 says a wave has a speed of 30 meters per second and a wavelength of 3 meters. What is the frequency? So wave speed equals wavelength times frequency. Divide both sides. We see the frequency is 10 meters per second. So number 4 says the period of a wave is equal to the time it takes for one wavelength to pass by a fixed point. You stand on a pier watching water waves and see 10 wavelengths pass by at a time of 40 seconds. What is the period of the water waves? So period is the time needed for one wave to pass by. Well, you saw 40 waves in 10 seconds. So that means a wave would need 4 seconds in order to completely pass by. So every 4 seconds, you would see a new wave. B says, what's the frequency? Well, frequency is the number of waves every second. So the number of waves every second. Well, if we see one wave in 4 seconds, that means that for every second, we would only see a quarter of a wave. So frequency is the reciprocal of the period. Period, or reciprocal just means 1 over something. So the frequency is 1 over the period. In this case, the period was 4. So the frequency is 1 over 4, or 0.25 hertz. And then the last thing says, okay, well, our frequency is 0.25 hertz. The wavelength is 3 meters. What's the speed? So again, speed is wavelength times frequency. Okay, so that is how to calculate those wave speeds. All right, so you'll complete the work page now. Any type of wave, whether it's light or sound or water, whatever, can go through these types of behaviors. So they can be reflected, meaning that they hit an object and bounce back. So any type of wave can be reflected. We call this imaginary line that's at right angles to the surface of the object the normal. So this is the normal right here. It's at 90 degrees to the surface of the object. The angle of incidence is the incoming light. So incidence meaning incoming light. So the angle of incidence is the angle of the light as it comes in. The angle of reflection is the angle as it's reflected out. The law of reflection says that these two angles are identical. So if light is coming in at 30 degrees angle, it's going to reflect at 30 degrees. Waves can also be refracted, which means it bends when it hits a new material, it hits a new medium, it starts to slow down. So looking at this little picture with the pencil and the cup of water, so light waves are traveling through the air, then they hit the water, that's a new medium, and it causes the light to slow down. And when that happens, it looks like the pencil is broken. The light has now bent, and so it looks like the pencil is broken. Diffraction occurs when a wave hits an object and bends around it. If the object is really small, it affects the wave a lot. If the object is large, there's less of an effect. So right here, a small gap causes a really big change in the wave. But a large gap does not affect the wave as much. So, interference is the combining of two waves overlapping to form a new one. There are two types of interference, constructive and destructive. In constructive interference, the amplitudes line up and the amplitudes end up being greater. In destructive interference, the crests and the troughs line up and they destroy each other. Their amplitude is less. So constructive builds up, destructive destroys. A standing wave is a wave that is stuck in place. So it's a wave that vibrates between two fixed points, and there's constant interference. This point where there's no amplitude is called the node. The point of the highest amplitude is called the antinode. Resonance is caused by an object absorbing energy at its natural frequency. So you might have seen videos of people or cartoons showing opera singers breaking glasses with their voice. And that can happen. You can find the correct note or the frequency that that glass vibrates at, and you're going to actually shatter it. And that's what the little video here on the end is. So make sure you watch this video here. All right, so you'll complete the work page, and when you finish, turn it in.